Hello everyone, welcome to the 12th webinar in the Joint Tran-SET webinar series, which will cover a variety of projects related to advances in the ultra-high performance concrete from three quite different perspectives. So today we are privileged to have three transportation experts presenting in this webinar. We will have 15 to 20-minute presentations. First, Dr. Kyle Riding will discuss the ultra-high performance concrete quality control testing. After that, Dr. Royce Floyd will present the ultra-high performance concrete and innovative concrete materials for pre-stressed concrete girder repair. And finally, Dr. Brad Weldon will present the field implementation and monitoring of an ultra-high performance concrete bridge deck overlay. So, without further ado, I will introduce our first speaker, Dr. Kyle Riding. Dr. Riding is a professor of civil and coastal engineering at the University of Florida. His research focuses on the durability of concrete structures and pavements, early age concrete structural behavior, concrete microstructure characterization and modeling, and novel cementous systems with a goal to enhance and preserve the nation's civil infrastructure. Dr. Riding has been at the University of Florida since 2016. Prior to coming to the University of Florida, he was one of the faculty at Kansas State University. Dr. Riding is currently the chair of the Precast Pre-Stressed Concrete Institute Concrete Materials Technology Committee and is a voting member of the Pre-Stressing Reinforcement Committee. He is also chair of the American Concrete Institute Committee 231 Properties of Concrete at Early Ages and is a voting member of ACI 201 Durability of Concrete, ACI 2007 Mass Concrete, and ACI 236 Material Science of Concrete. He is a licensed professional engineer in Florida, Kansas, and Nebraska. So Dr. Riding, I will turn it over to you now.
All right, thank you. Let me share my screen here with you. All right. Okay, can you see my screen here?
Yeah, we can see your screen and we can hear you. You can start right now.
Okay, great. Okay, so I'm going to talk about quality control testing for ultra high performance concrete. Many of you are familiar with UHPC, and that's why you're listening to this. If you aren't, ultra high performance concrete is a fantastic material with lots of different applications in structures and infrastructure. You can see some of these examples. One is joints. They're used an awful lot for closure pours nowadays. The picture in the middle is that of pile. They're used H piles and other types of concrete piles. They're thought to be cost effective for marine environments. Bridges, picture top right of a pedestrian bridge, and then even hybrid structures with UHPC and self-consolidating concrete together. That's a bridge made in Florida on an FDOT project. So UHPC has a lot of different benefits. You can use it to reduce the amount of steel reinforcement, use it to make your concrete members lighter, and significantly improve the durability of your concrete. This is especially important for environments that have chlorides, like marine environments or bridge decks or other areas exposed to it. Okay, so we know it has a lot of different benefits and applications. You're going to find a different definition for UHPC depending on who you talk to. You'll find some definitions that have it at 150 megapascal or about 22 KSI compressive strength. Others that define it at about 120 megapascal or about 17.4 KSI. FDOT, right now we're working with the Florida Department of Transportation on looking at where these limits should be. But most of the discussions you hear about compressive strength, how strong can we make it? Whereas really the real benefits of UHPC come in the tensile strength and preventing it from cracking and giving you good properties from a structural tensile point of view. So how do you measure these properties? We're not used to measuring regularly tensile strength for concrete. In most structural designs, we basically ignore it and assume that our reinforcing steel is going to carry the tensile loads. Well, if we're going to take advantage of UHPC and its high tensile properties, we have to be able to measure it properly. So one test that's been developed by the Federal Highway Administration is a direct tension test. It's based on a 2-inch by 2-inch cross-section sample. It's 17 inches long with aluminum plates glued on the side to give it that dog bone sort of effect. And it's pulled with a closed loop displacement controlled machine with a compressometer in the middle. And this gives you pretty directly a stress strain curve where you see multi-cracking in good UHPC and most of the time and hopefully you'll see strain hardening behavior and multi-cracking as you see on pictures in the right upper hand corner where you get these tensile failures. Okay, so that's one test method. It's expensive. The equipment is not very available currently and definitely not available at most local laboratories. Another test that's more widely used to qualify ultra-high performance concrete and its tensile properties is ASTM C1609. It's a flexural test where we basically put a UHPC sample in flexure, a 4x4 inch cross section is typically used, and based on the load displacement curve, you'll see toughness parameters calculated and a flexural modulus calculated as shown in the equation. Okay, so you get to one of these tests. They work really well for qualifying your material, but both of these require expensive closed loop displacement controlled systems to get good results. So what do you do for quality control? So many times no tensile testing is done at all. They just rely on the compressive strength testing and rely on the tests that were done during qualification. We assume that it's going to be okay. We assume that the right amount of fibers have been put in, which is a big assumption since at many plants, they're added manually. It's very easy to miss a sack of fibers. PCI in the design guide that we're working on for UHPC materials is considering requiring 3 beams per day of the flexural testing with an additional 3 beams if you go over 25 cubic yards. This is pretty expensive testing for plants to do on a regular basis. So it's somewhat cost prohibitive to do. So we want something that can be done at plants or local testing facilities that don't have this expensive equipment to be able to do more quality control and more frequently to be able to characterize their UHPC and make sure that they're getting what they expect. So the ideal quality control test would be something that can accurately characterize the tensile strength, gives you a measure of the ductility or toughness of the material, very important, not just the strength, and can be done with commonly available equipment at precast plants or local testing labs. We also want it to be simple to perform. You don't want to have a PhD to perform this test. Okay, so let's look at a potential test here. It's called the double punch test or Barcelona test. It was popularized, well, it was originally developed in the 1970s as a test to measure plain concrete tensile properties, but it was adapted recently for ultra high performance concrete or fiber reinforced concrete by a group in Barcelona, Spain. And in this case, you have a concrete sample where you have 2 punches, steel punches that you place on the top of the concrete sample. And then when you put it in compression, you get cones of failure that form underneath those punches. And then when those form, as you continue to compress the punches together, the punches come inwards, and because of wedging action of those cones, it forces the concrete to outwards. Okay, so when it does this, you get a failure as shown since ultra performance concrete is fiber reinforced, you do get multiple cracks there because you're able to distribute the cracks. That's what you want to see. And when you look at diagrams where you try to calculate the stresses, you can get an equation that allows you to calculate the tensile stress based on the load applied to the punches. Traditionally, the displacement part has been measured using the change in circumference of the sample using an extensometer. It works really well. They have good use and history of use of this in Spain. There is an ASTM in works that's being used to develop this test. It's still very complicated. You still need a displacement controlled closed loop machine to do this. And the extensometer costs on the order of about $6,000, not to mention the data acquisition to record this. So it's still really out of the realm of capabilities for most precast plants and local testing labs to run. Plus, it's somewhat complicated to run comparatively because of the data acquisition and logging. So one of the things that was realized in this testing in Spain was that instead of measuring the circumference, you can get similar type of information by just measuring the axial displacement of the machine. And so you get a problem in plain concrete or concrete that's strain softening where you get basically no displacement measured by the extensometer and the circumference until you get a crack that forms. So you get an axial displacement that does not relate to the circumferential displacement until the cracks forms, and then you get a big jump in the circumference measurement, and you get a linear relationship between the circumference measurement and the axial measurement. In ductile materials like UHPC, however, you don't get that big jump in displacement when a crack starts to form. These cracks form more gradually, and so you get basically an axial displacement with zero circumferential increase until a certain point where you start to get micro cracking, and then you get this linear relationship. So we have a very nice linear relationship in ductile materials like UHPC after you get the first crack to form. So this is very handy. It gives us a way of relating the two and giving us hope that we can use an axial measurement, which is much easier and cheaper to do than a circumferential movement. Okay, so the next step that we need to overcome is these closed loop machines that are used in the Spanish standard and the draft ASTM standard. So most plants don't have this, they just have a simple compression machine. Now most compression machines are actually displacement controlled machines, they're just not closed loop. This means that after the peak compressive load or peak compression, as the load starts to decrease, you get an elastic release of the strains in the walls of the testing machine, which increases the rate of displacement of the sample. Now, this is a big problem if you have a material that cracks and is not ductile. You get a sudden release of energy and you get a sudden impact loading once a crack forms in non-ductile samples. And this leads to a lot of problems. The UHPC, however, if it's ductile, you don't get this sudden release of energy and impact loading when you start to get cracking. It gives you a very nice smooth response. At least that's what our hypothesis was. So we started testing a program where we used, you can see here, some string potentiometers to measure the axial displacement of our machine and measure the load, and we're able to capture a load axial displacement curve 4 samples tested in our simple compression machine. Okay, so we wanted to answer as part of this, can this simplified test be performed in a simple compression machine for QC purposes? Does it work? And is it going to give you reliable results, even though it's not a closed loop? The next thing we wanted to look at is what are the parameters of the test that you have to control and specify that are going to cause issues. So we wanted to look at finishing process. Do you have to grind these samples flush, or can you just trowel them? That makes a big difference in sample prep for labs. How to cast them. That was an issue we wanted to look at. Punch alignment, if you're off a little bit with the punches, does it make a difference? And the load rate, especially the load rate, because the load rate on a lot of these machines is a little bit harder to control. You don't get a dialed in exact 1 millimeter per minute displacement. So we wanted to look at these and then look at how our tests results from our simplified double punch test compared to the more complex and expensive direct tension and flexural tests. Can we use this as a quality control test? Maybe not qualification, that's okay. For qualification, you really have to do that once, and so you can afford to spend more money on that test. But as a quality control everyday test, can it be used? So our ruggedness test, we looked at the casting method, filling it with a scoop versus filling it with a bucket very fast. We looked at grinding the samples versus not ground. We did fast versus slow loading rates. You're talking about 2 to 4 times loading rate, and a 5 millimeter off center of your punch. So we controlled all of these variables in a testing matrix specified in ASTM E1169 to see if these factors were statistically significant. And we looked at, with our test, the max stress. We looked at the toughness, or the area under your displacement calculated stress curve, and we looked at the displacement location at which the peak load occurs. So with our ruggedness test, we found that the displacement at peak load was significant if you didn't grind the samples, and that makes sense because you have to locally crush the sample at the surface in order to really dig in and seat the punch. But it didn't affect the stress or toughness. We found that the scoop versus bucket was very significant. How you make these samples really matters. If you're filling it with a scoop, you're doing scoop by scoop, you're basically filling the sample layer by layer. And what we found is that the fibers tend to align in the horizontal direction with thin layers that you place. Each thin layer self-levels out to a thin layer, aligning those fibers in that horizontal direction, and that gives you much higher tensile strength because scooping it gives you a really preferred orientation, helping to boost your strength. So you do need to fill these rather fast and all in one placing from, say, a bucket. The load rate didn't matter, even that big of a load rate. You know, we see a lot of talk about how the displacement rate needs to be controlled precisely. We found it was not statistically significant in this test, and that's because of the ductility of the sample. A lot of those issues matter less when you have a ductile sample. You're not getting impact loads, and that elastic release isn't affecting as much. And the centering was not statistically significant either. Centering is actually pretty easy to control. You can use templates to help you get it centered right. Okay, our next idea, you know, again, most of these labs don't have the ability to collect string potentiometer data, just like they don't have the ability to collect the extensometer data. So what we did was numerically, we looked at our continuous data and we selected points off of it. So say you take these readings manually, okay? You have a dial gauge that you read off of to read the displacement, read the load and displacement. If you were to select these points manually and then build your curve in that point, say every 0.025 inch of displacement, how does that affect the toughness results that you're getting? The peak strength you can get because the machines typically have a method of giving you the peak results independent of you keeping track of it during the test. So that's not a problem. But the area, we were concerned that would matter if you simplified it further. We found that as long as you're taking results about every 0.025 inches, it only made a difference, a deviation of 1.5% from taking continuous measurements. Very little difference, and gives us confidence that you can take these results manually, writing these results down. And in fact, we've taught undergraduates in our laboratory how to take these. It's similar to how elastic modulus tests are performed manually. You know the load, you write down the load and the strain value in the compressometer when it's written. Well, in this case, you write the load down. And for us, this means basically you have your punches, you write the load down, and then you have a displacement gauge. You can buy these pretty cheap at the hardware store. At most, even a fancy one's a couple $100. So you can run this, plants can run this in their compression machine without any real issues. So we looked at different fiber percentages for ultra high performance concrete to look at how they affected the results in this double punch test. And we found that 2 different types of fibers, that you get very different results if you just look at the stress, basically the strength or maximum strength of your material. And part of this is because you can get a very high strength, failure strength, just from the first cracking load, basically the strength of your cementitious paste system, even without the fibers. You can get a very high load, but then it cracks and you get no strength, no residual strength after that. And that's why you really need a measure of toughness or ductility. And so with our fibers that were not giving us a ductile response, the double punch test was able to nicely pick that up and picked up the toughness with our straight fibers pretty well. Okay, so if we compare the results of our double punch test compared to our direct tension results and our flexural test to see how it performs, we find that we get very nice correlations between the direct tensile strength in double punch and our direct tensile results. We get the same with our direct tension versus our flexural. You get nice correlations no matter which test method you use. You just have to be careful that with the flexural test, you're really getting a modulus of rupture, not a true tensile strength, just using that simple equation. So something to be aware of. We find that when we can compare the flexural modulus of rupture with the double punch test tensile strength, you get very nice correlations. Again, you just have to be aware of that increased because of the flexural modulus of rupture. When we look at direct tension ductility parameters, so we compare, say, the tensile stress at 0.05 strain or the direct tensile toughness, get, again, excellent correlations. These are on the same order of R-squareds as when you compare the direct tension toughness to the flexural result toughness. Very good, nice results. So if we look at a summary of our tests, first thing we can say is you really have to have a measure of toughness and ductility for UHPC for it to be valuable. Otherwise, you're just measuring the a lot of times the first cracking load, or you could accidentally. So for our ideal QC test, looking at our parameters, we find that we can accurately characterize the tensile strength with our materials. We've got very nice correlations with the direct tension strength. It gave us a very nice correlation with more expensive measures of ductility and toughness. You can do it with commonly available equipment at precast plants, and it's pretty easy. We're having undergraduates perform it at our lab. We would recommend that you do a round robin, that a round robin study be done, and just to get the precision and bias. But we feel that this test method could be used as a quality control test at the plant. With that, just acknowledge FDOT for their support and advice and help. With that, take any questions that you have.
Perfect. Thank you very much, Dr. Riding. That was very informative and interesting. So now I will introduce our second speaker, Dr. Floyd. Dr. Floyd is an associate professor in the School of Civil Engineering and Environmental Science at the University of Oklahoma. He has 12 years of experience in research related to performance and strand bond behavior of pre-stressed members cast with self-consolidating concrete, lightweight self-consolidating concrete, and ultra-high performance concrete. He teaches courses on engineering mechanics, reinforced concrete, pre-stressed concrete, and structural wood design. He is a member of the American Society of Civil Engineers Precast, Pre-Stressed Concrete Institute, and American Concrete Institute, and he is a registered professional engineer in Oklahoma. So Dr. Royce, I will turn it over to you now.
All right, thank you, Momin. So today I'm going to talk a little bit about a project that we've got ongoing with the Oklahoma Department of Transportation that's looking at ultra high performance concrete, but also some other innovative concrete materials for repairing pre-stressed concrete girders and pre-stressed concrete bridges. So if we go to the next one here, think about kind of the motivation behind the study that we're looking at, especially in Oklahoma. We have a lot of bridge deck joints that are in pretty bad shape. And here I've got a couple of pictures of some of those deck joints that are deteriorating, that we have some perforations through the sealant material within the deck. And if you look at just Oklahoma, you line up all these joints end to end, we have somewhere in the neighborhood of about 50 miles of joints that are currently in need of repair and rehabilitation. Well, not just fixing those joints is necessary, but as they're damaged, they're letting chloride permeated water go onto our girder ends within the bridge, and it's causing a lot of damage and corrosion within our precast girder end regions, where we have our major location of pre-stress transfer. We have high shear forces, and we've seen in some testing of full-size girders with this type of corrosion damage that we can even get deterioration of the bearing regions under service load levels. So this can cause some serious issues in terms of the life of our bridges over time. So there are a lot of ways that we could eliminate these problems. One of them is to reduce the number of deck joints to begin with. And in a number of bridges in Oklahoma, this was done by creating continuous spans between our precast members with individual continuity connection blocks. So the ends of the girders would be connected using extended pre-stressing strands from the end of each girder, some mild steel rebar in some cases, and then a concrete block cast to connect the ends of those two girders, which would make them continuous for live load. This has led to a lot of issues in Oklahoma because almost every one of these bridges has cracks through those continuity connections that are caused by restrained shrinkage and creep as the bridge beams experience losses over time. So in looking at these two issues, we thought UHPC has some great potential for repair and rehabilitation of these two particular locations of girder end regions that have been damaged, as well as these cracked continuity connections. And as has already been discussed, UHPC is a great material, has a lot of potential for a lot of different things. It's characterized by its high compressive strength. Here, using a more general definition, between about 18,000 and 30,000 KSI is what you will typically see as UHPC, and then also has that great post-cracking tensile strength that we discussed in the previous presentation. It's very flowable and is able to get into some complex shapes, which is wonderful when we're talking about repairs and rehabilitation. And we'll talk about that a little more later on in this presentation. But it also has a very low to negligible permeability, high freeze thaw resistance, just an overall great durability, which can help us to repair some of these damaged regions and to encapsulate them, to prevent further damage in the future. So in terms of what has been done in the past relative to UHPC repair and rehabilitation, within Oklahoma, we've done some study on expansion joint headers and actually done some field implementation using UHPC to repair around the expansion joints, which was kind of the motivation of this project. In other states, there's been a lot of work done with UHPC link slabs that are used both in new construction and even removing some of those joints in the deck and spreading out the joints to the end of the bridge. Previous research has been done on repairing steel girder ends with UHPC, so kind of as an encapsulation with shear studs on the girder web to strengthen the end of a corrosion damaged steel girder. And then some recent work has looked at using UHPC as kind of a patch repair on the ends of pre-stressed or precast pre-stressed concrete girders. So this webinar is primarily focused on UHPC, and that is the main point of a lot of the work that we've been doing. But in fairness to the rest of the project, we've also been considering some other innovative concrete materials, such as fiber reinforced self-consolidating concrete. So we have very flowable concrete that compacts under its own weight. It's also easy to cast, can be cast into complex geometry and congested reinforcement without the need for vibration, and then includes fiber reinforcement and an expansive agent to reduce and prevent any detrimental effects from differential shrinkage between the repair and the original material. This material has been used in some different applications, such as some retaining walls in Montreal, some bridge piers in the US, and then some of the work that's been done here at OU related to bridge girders was to take a full-size ash toe type 2 girder that had been taken out of a bridge and been tested to complete failure in flexure and shear at each end. And then the damaged sections were actually jackhammered out, which you can see here in the picture on the right in the red outlined region. That concrete was removed. It was replaced with this fiber reinforced self-consolidating concrete that was cast through holes in the deck to simulate what you would do in the field, and then was retested in the same configuration. And we were able to restore about 80% of the capacity with that fiber reinforced self-consolidating concrete at one end post-tensioning to restore the pre-stress, and at the other end not post-tensioning, and still able to get around 80% of the original capacity. The other material that we were considering in this research is magnesium alumino liquid phosphate, or MALP concrete, which is a two-part system that has a magnesium alumina aggregate dry powder and a mono aluminum liquid phosphate activator that are mixed together. It's very rapid setting, has a very rapid strength gain. It's great for low temperatures because it will still set and gain strength rapidly even when it's very cold. It also chemically bonds with both the base concrete and with itself. So you get a very nice interface bond between the two materials. It has potential to reduce the halo effect in terms of corrosion in the base concrete, and it's been used successfully in a number of states for repair applications, and at this point, including Oklahoma. All right, so the objectives of kind of our overall project was to examine UHPC, FR-SCC, and MALP concrete as a repair material for girder end regions with induced shear damage, which is what I'm going to talk about most in this presentation. Girder end regions with simulated corrosion damage, which is somewhat still ongoing within this project. And then also looking at repair and replacement of those continuity connections using some of these materials. And then finally, to actually look at the effectiveness of using UHPC as a continuity connection replacement in a full-scale in-service bridge. So in terms of looking at the in-region repair, we used a approximately half-scale pre-stressed concrete girder specimen that had two half-inch special pre-stressing strands. It had a composite deck section that was designed to simulate a half-scale bridge deck. But we increased the depth and shortened the width of that section so that we could get the same flexural capacity with a smaller overall section. It included shear reinforcement that was designed to produce a flexural failure at mid-span. We cast these specimens at Fears Lab on the OU campus. We ended up casting them one at a time because of the pandemic restrictions and other projects getting behind. We didn't have as much space as we would normally have to pre-stress 2 or 3 of these at a time. But either way, we would put together the reinforcement cage and the formwork, run the strands through, pre-tension the strands with our pre-stressing abutments that are shown here, cast the specimens using a self-consolidating concrete mixture that would gain a strength of about 4,000 PSI in 1 day, release the pre-stress, and then 28 days later, cast the decks on top of the beams. So once we had the specimens constructed, we were going to test those to failure in shear and then repair them using these 3 different repair materials. The FR-SCC that we used was developed through previous research at OU. Former student Corey Workman back in 2016 kind of did the initial work on this, but it also built on work of my colleague, Dr. Jeff Voles from Missouri S&T originally. And the mixture is a Portland cement concrete with fly ash and then type K expansive cement, which is the product component. It used a 3/8 inch river rock along with fine aggregate. We used polypropylene fibers. It had entrained air and then enough high range water reducer to get the flowability that we were looking for, which was in the range of about a 28 inch slump flow. We also included citric acid within the mix to control the set, because the component cement does lead to an earlier set time than what we would get with just a pure Portland cement concrete. The UHPC that we used in this project was a non-proprietary mixture that was developed here at OU by some former students, which was published by Alumni in 2019. But it includes a Portland cement mix with a 30% replacement with slag cement, 10% replacement with silica fume. We used 1/2 inch steel fibers at 2% by volume in this mix. And then again, high range water reducer sufficient to get us about an 8 inch slump flow. The mount product that we used was a proprietary product marketed by a company called Phoscrete. And we used the same materials throughout for each of the different aspects of this research, whether we were looking at the shear induced damage, whether we were looking at the corrosion induced damage, or damage to those continuity connections. So specifically for the in-region repair for shear damage, or you could think of this as shear strengthening, we did an initial load test to induce a bond shear failure. So again, close to the in-region, potentially could be affected by corrosion at the ends. We loaded to failure, and our failure criteria was based on the maximum deflection as well as the anticipated load. Afterwards, we mapped all the shear cracks so that we could compare to the post-repair load test that we would do eventually. And then once we had our induced damage, we went in and encapsulated the end region using either the UHPC, FR-SCC, or MALP concrete. We roughened the surface using a grinding wheel, basically, trying to simulate what you could do in the field. And then we, as shear studs, used concrete screw anchors that were just basically Tapcon concrete screws. We designed a pattern for those shear studs that would span the entire repair area, but would be offset on either side, so we didn't have two screws at one point on the web. And then we designed the number of screws that were needed by looking at a strut and tie model of the end region and the compression force that we would need to carry to get the full shear capacity. You can see on the right our repair sections. For the UHPC, we used a minimum thickness of 1.5 inches on the bottom flange. We had 2 inches below the beam, and then we used a constant cross section all the way up. So we had, a 4.5 inch thickness on the web, and then a 3 inch thickness on the top flange of the beam, and we went to the bottom of our simulated deck. For the FR-SCC and the MALP concrete, which had a lower strength, so I should say the UHPC is about an 18,000 PSI material, the FR-SCC is about 6,000 PSI, and the MALP concrete is about 12,000 PSI. So for those two lower strength materials, we increased the thickness of that section out to 3 inches on the bottom flange, and again, constant rectangular section. So this shows some of the specimens after the repair. So the UHPC on the left and the FR-SCC in the middle both had a very smooth finish. We cast both of those specimens by pouring material into the forms from one side, letting it flow underneath the beam, and fill the other side until we completely filled one side, and then we would shift to the other side and top off the repair. For the MALP on the right, we were mixing individual batches of a bag of material and a bottle of activator at a time, which is the process recommended by the manufacturer. That resulted in a number of different batches. Again, it sets really quickly, so you can see these pore lines in between the layers. We allowed it to flow under the beam and then started alternating sides in terms of casting the material. Because this chemically bonds to itself, we didn't anticipate the pore lines being an issue. That was an expected result. It just doesn't look quite as nice as the other two because of that. We then completed post-repair load tests using the same configuration that we did pre-repair, which was a single point load about 4.5 feet from the end of the beam. And these pictures are all post-testing. So you can see the cracking patterns in each one of them. You can also see that there's not a lot of cracking that was observed. You have to remember that there is cracking underneath the repair that was already there. But in each case, we primarily saw new cracks outside of the repair. In all cases, those cracks actually extended past the load point in terms of shear cracks, which was a little bit unexpected. For the FR-SCC and the mount concrete, we did see a crack right at the interface between the repair and the beam. And then, for all three repairs, we saw very little cracking actually in the repair material. We saw just a few cracks in the UHPC and FR-SCC repairs. We didn't see any in the mount concrete for either specimen we tested. If we look at a comparison of the pre-repair and post-repair load tests, which is shown here, we can see the blue lines for the pre-repair tests all are pretty indicative of bond shear type failures, where we have this bond loss that's causing us to have a more or less consistent load, but it's not a yielding type failure. It's a bond shear beam failure. Then we repair the specimens. In each case, we can see that we have an increased stiffness because, of course, we're adding cross-section to that repair. And in all cases, we had an increase in ultimate load and a shift to more of flexural behavior for the beams after we repaired them. If we look at the post-repair load test for all the specimens, we see very similar behavior early on. So very similar stiffness at the beginning of loading, and then the FR-SCC and the mount concrete are very similar, where the UHPC gave us the highest load after repair. If we look just at maximum loads, for all specimens, we increased capacity by about 40% compared to the original non-strengthened case where we had that bond shear type failure. All right, so I'm going to spend just a few minutes talking about a different aspect of this project where we actually did a field implementation replacing in-service continuity connections with UHPC. This was on a 5-span bridge in western Oklahoma. The middle 3 spans were continuous. They're about 80-foot spans in each case. And those 3 spans were connected using these individual continuity connections. Every one of them had these cracks that are indicative of the effects of restrained creep and shrinkage within the beams. And initially, we did a load test of the bridge before we repaired it to kind of get a feel for the initial condition and the level of continuity that was present. We measured deflection on span 4, which was the continuous span closest to the north side, using laser distance measurements and then plumb bobs. We loaded it with 2 fully loaded dump trucks because the spans were pretty short. If we put a larger truck on there, we wouldn't get the kind of deflection effects that we were looking for. Then the joints were demoed by the contractor doing the rehabilitation on this bridge. We installed some strain gauges in an exterior joint and an interior joint between spans 3 and 4 so that we could look at deformations after repair that we couldn't look at in the pre-repair load test. Then the joints were constructed using the proprietary UHPC ductile. It was placed through a 2.5-inch hole in the deck into each of those joints. So it had about a 5-foot free fall into each joint. It was a little difficult to place it through the hole, and I'll tell you a little more about that here in just a second, but we produced a very nice replacement joint using that UHPC. So you can see from a couple of different angles. We monitored those joints for about a year. After that year, they looked as good as they did the day they were cast. We didn't see any signs of distress around those joints. Here on the right, you can see at the top of one of those joints, there is some airspace, which we think is a result of air escaping, causing some settlement after casting, just because we only had the one fill hole that was fairly small and the air didn't have any way to escape quickly. All right, so just quickly looking at the post-repair load tests, we use 6 different loading stages to characterize all the different possibilities for continuous behavior. And if we, look at both measured before and after, as well as calculated for assumed simple spans before and continuous spans after, we see all the signs that we're getting the continuous type behavior that we anticipate. So in conclusion, all 3 repair materials that we used provided an increased capacity when used to encapsulate a shear damaged end region, with UHPC providing the greatest increase in capacity, even though it had the smallest repair thickness. Those specimens exhibited less cracking than the initial beams, which could lead to some improved longevity if we encapsulate the ends of some of these beams that have damage. And then finally, we successfully used UHPC to replace some existing precast concrete girder continuity connections that appears to be functioning as expected. We still have some work to do that's ongoing, but I'll end here because I think I'm a little over time, and say thanks to all those that sponsored our work and worked with us on this project.
So perfect. Thank you very much, Dr. Royce. We really appreciate your presentation. So now I will introduce our last presenter, Dr. Brad. So Dr. Weldon holds a bachelor from the New Mexico State University and a master's and PhD degrees from the University of Notre Dame. Dr. Weldon conducts research in bridge design and behavior, structural engineering, earthquake engineering, and innovative sustainable structural materials. Dr. Weldon's research expertise is in large-scale testing and evaluation of structural systems under various loading scenarios. Furthermore, Dr. Weldon has significant experience in the inspection, evaluation, and testing of bridges. He has conducted significant research on concrete, timber, adobe, and masonry systems. So I will turn it over now to Dr. Weldon.
Thank you. Let me see if I can get my screen up here.
Okay.
All right, should be seeing my screen now, is that correct?
Yeah.
Perfect. So today I'm going to talk to you about a project looking at the use of a UHPC concrete bridge deck overlay. So this project, actually the PI on this project is Craig Knudsen, and I'm the co-PI. And also we've had several students working on this project that are listed there as well. So we're looking at using local materials for us. So just a little bit of background into this project. We've been working with the New Mexico Department of Transportation for quite some time to develop UHPC with local materials. So kind of as a starting off point, we had some material that we developed and we kind of adjusted those mixture proportions for the application of overlays. So that was kind of our starting point for this project. And so I'll give you a little bit of background as we go through this on some of the laboratory tests that we've conducted as we started the overlay project. And then we'll talk about some of the field implementation, what's going on with the project right now, just a brief summary of everything as we go. So the objective of this overall project was to assess that potential of using this locally developed UHPC as an overlay material. And so we did this in first starting with our laboratory studies. So we did a lot of different studies there. And then now we're implementing it into the field. And as the project continues, we'll be monitoring the behavior of that overlay as the project continues. So starting with the laboratory studies, we went through a lot of different tests to get to the point where we felt comfortable implementing it in the field. And we started with looking at bond. All right, so we did several different bond tests to verify our behavior there. We looked at slant shear tests, splitting shear, and direct tension tests. And what we found was that the performance of the UHPC, it bonded very well to the substrate surface conditions. We also looked at a lot of different surface textures, how those different textures affected the behavior of those. And we found that, really with minimal surface preparation, we got really pretty good levels of bond. So after some tests, we then put this UHPC on a girder that we had in the laboratory. So we actually put a 1-inch overlay on this girder you can see here. And then we subjected this girder to 1,200 load unload cycles at what we greater than expected service load conditions. So meaning that we displaced it much larger than what we'd expect to see under truck loading, essentially. So after those 1,200 load unload cycles, the overlay exhibited no visible indications of distress or any debonding issues on the girder. We then took the girder to failure. We tested the girder to failure, and even after we took the girder to failure, we really didn't see any significant signs of distress. We did have a few isolated debonding locations, but that was, like I said, after the girder failed. So we felt comfortable that we were able to get the bond that we were wanting. We also looked at shrinkage, and so we looked at early age shrinkage, and we did this just because as the shrinkage occurs, we know this is going to develop stresses between the substrate and the overlay. So we wanted to make sure that we could accommodate that. We had an idea of what we'd expect in the field, and so we looked at early age shrinkage by looking at small prisms. Essentially, we were monitoring the strain that was being developed over the first 7 days of that for the early age shrinkage. So you can see the test setup there. And so what that enabled us to do is just monitor and capture those deformations in the UHPC specimens. We also looked at a little bit longer term shrinkage. So again, looking at prisms, we took length measurements for up to 28 days after demolding. So we have a little bit of idea of what goes on in a little bit longer term as well. So then we also wanted to double check and look into the temperature and shrinkage effects, or the combined effects of these. So we conducted some slab tests. So these slabs were 3 feet by 2 feet slabs, and they varied in different thicknesses. So we had 4 inch up to 6 inches thickness, also very different reinforcement ratios. So we looked at the various reinforcement ratios and how this affected the behavior. We monitored for each of these slabs for over a year, right? And so within that year, we wanted to go through those so we could see the load and temperature cycles. Right? So we had vibrating wire strain gauges embedded in these, as well as foil strain gauges on the reinforcement as well. And so you can see down here in the corner, we have just our time versus microstrain. This is up to about 100 days. But we were able to capture the behavior of that, look at what stresses were being developed at that interface, and kind of characterize what we'd expect under both the temperature and shrinkage conditions as they were exposed to the environmental conditions. So based off of all of this, the laboratory testing, we kind of identified that we had adequate bond strength. We saw that with all of our different testing that we did on both the small specimens as well as the girder test. With the early age shrinkage test, we showed that the majority of that occurred in the plastic state. So we didn't really expect this to contribute to the bond stress too significantly at the early ages as it was pretty young concrete. And then we monitored those temperature and shrinkage slabs for over a year, and we had no issues with debonding observed during that time. So at this point, we felt comfortable to move to the field implementation with working with the New Mexico Department of Transportation. So the bridge that was identified, right, was bridge number 7032. It was located in Socorro, New Mexico, and it's a 2-lane bridge that's approximately 300 feet in length. And you can see this is the bridge here in that lower corner there. So the plan was to put the overlay on this, and in doing so, they were also going to replace portions of the deck. And so this isn't quite the traditional method that you would just apply the overlay on the deck. They actually were doing some additional work on this as well. Okay. So as we begin this field implementation, as part of the requirements for the contractor, we had to do a mock-up. And so we were there looking for, to look at quality control, look at surface roughness and surface preparations on this. We did some bond tests with this, and really just to address any challenges that we had. And one of the biggest challenges actually came really early on when we had to change the fibers that, as many of you might be aware, the fibers that were produced in the United States changed, and so we had to go to a different fiber and make some modifications there. And I'll address that a little bit here on a few later slides. So initially we were starting out with just working with the contractors doing one mock-up slab, and these slabs were 20 feet by 20 feet. With this, the concrete that was going to be used, the HPD concrete slab, the deck that was going to be placed. These were unreinforced, and they were field cured for a minimum of 7 days prior to putting the overlay on the mock-up. After curing, the slabs were thoroughly pressure washed and cleaned just to ensure that we have good surface for bonding. Within these slabs, we also did a couple of different things. We looked at different surface roughnesses. So in some cases, we actually left it partially flat. We looked at different types of surface roughness, and to just kind of look at the bond strengths that we got to this field application. So we were kind of running a little bit of an experiment with and looking at that surface preparation as we were doing the mock-ups with the contractors as well. So we started out with just planning for one mock-up. We ended up doing 3, and this is kind of comes into some of those challenges that we see as we take that, the stuff from the laboratory and then you take it into the field. So the first mock-up, essentially we were there. We worked with the contractors there to cast the UHPC. However, we had some issues with that. The moisture content in the sand was not properly accounted for. And then a different super plasticizer was used than what was specified. So we actually didn't get set for about 7 days with this product. So we immediately knew that we had to do something else with this. So mock-up 2, we reused the mock-up 1 slab. We didn't really place the UHPC on that just because we knew issues were already there. Within this, we had the 5 batches of the overlay material that was placed. And other challenges that we were associated with, the mixers, mixing times, getting the concrete down and quickly. Summer conditions in New Mexico at the time were well above 100 degrees Fahrenheit, so we were definitely dealing with temperature conditions and just making sure that the concrete was placed, cool enough and so forth. So we addressed some of those issues, and then we ended up doing a third mock-up. And so this one had a slab that was the first polished, and we had a new slab constructed for mock-up 3. And again, we cast 5 batches of the overlay material. And in this case, we did notice that the separate surface preparation wasn't consistent again. So we again looked at the bond as we were planning on. So after the third, and during these mock-ups, we were always looking at workability. We were looking at slump, spread, mixing times, and so forth, just making sure that we had consistency, getting the training there for the contractors getting used to the material because it is different, looking at how quickly things were placed. So we looked a lot about the workability and just the placement of this, the overlay as well. Right. And then we also looked at strength gain. So we looked at, I'm just showing the compressive strength gain, but we also looked at modulus of rupture and a few other properties of the material. And here you can see, as Dr. Wrighty and Dr. Floyd both mentioned, that the definition of UHPC is typically about 70,000 PSI or greater. When we had to make the change to the fibers, we had to kind of give up some of that strength, which we were okay giving up that strength, but because of that, we're a little bit lower than that definition now of that UHPC minimum. So you can see our strengths are about 14,000 PSI on this right now on the mock-ups. So we also did the pull-off test. So we went out and poured several specimens and did some pull-off samples. We tested this and looked at the bond behavior of that. Some of the cases were a little bit lower than what we wanted to see with the field. So we went back and we did some laboratory tests as well. And so with the laboratory test, we were able to identify really key elements that were causing us issues in the field so that we could address those issues, work with the contractors in the New Mexico DOT to make sure that we get the bond that we're looking for. And so you can see here, these are just, we took the girder that had actually been tested, and we did some bond tests there, and we also had some additional specimens that we cast and looked at the bond on those as well. So at that point, we felt comfortable that we have addressed a lot of the issues that we were concerned with, made sure that we were happy moving forward. And then we started working back on the bridge now. And so we've been placing the sensors on the bridge. So we have strain gauges and thermocouples that we're working on right now. These will be inside the box girders, embedded in the HPD, the deck, and then embedded in a UHPC overlay as well. So we're looking at all these different locations that we're putting this in. Currently, we have 13 locations in each of those different locations, and you can kind of see here, we took the cells and identified which cells that we thought were going to be best for monitoring, give us the results that we were looking at shrinkage, looking at temperature effects, and so forth. And so this is kind of where we've chosen these locations here that you can see in circles on the plan view, and then looking at the cross-sectional view there, you can see that we chose the interior boxes there for the monitoring as well. And so the idea with these were that we wanted to do our best to kind of vertical profile. So you can see down here, we're trying to align the strain gauges along the cross section, so we get a strain essentially distribution along those three different materials: the existing concrete of the box girders, the HPD concrete that was just cast, and then the UHPC overlay, so we could look at the strain profiles in the materials. We put 2 strain gauges at each location, so we're looking at both transverse and longitudinal behavior. So you can see there we have the concrete gauges on the interior, and then we have the steel strain gauges that were embedded into the HPD layer. So the current status of where this is at. So we, about, I think a week and a half ago, they cast the HPD layer on the second lane now. So the deck concrete is now cast. We're currently working with the NMDOT to prepare to put the UHPC overlay on. And so we kind of where the project stands to date. So these are, like I said, these are the students who were out there last week working with the contractors on this, taking measurements. We do have a little bit of data collected. This is just raw data, so don't take it for anything more than just data that's been thrown on a graph. Nothing really that we processed it or anything yet. We just took a snapshot. This is data that was shown from the West Lane casting. It was, I think this is a 12-hour period, just like I said, a snapshot. So we are collecting data on the behavior of the system right now. It doesn't have the overlay on it, and so we'll also, collecting this data over time as we move forward with the project. So just to summarize everything, right? Transferring the UHPC technology to the field resulted in some changes to the mixture proportion. The steel fiber product was something that we had to change very early on. So we had some changes to the mixture proportion that did reduce the specified compressive strength. But like I said, we were willing to give that up as long as we were able to keep the other properties that we were needing with the overlay application. We also had to go back and make sure that we had the surface preparation correctly. We did see some lower bond strengths than we anticipated. We found those key elements that really played a big factor in that, and we've addressed that with NMDOT and working with the contractor to make sure that we have those issues taken care of. The mock-ups have been critical, and we found this in both projects that we've been with, bridge projects that I've worked on with the NMDOT with implementing UHPC is really those, mock-ups really do allow for the challenges to be addressed, training for the contractor, because it is a different material. Sometimes they don't, not seeing concrete that's much drier. People start adding water without really knowing what it's going to do to the mix. And so that training is very important. And that proper surface preparation is going to be required to achieve the bond strength that we're wanting. We've installed some of the gauges on the bridge. Right now, like I said, we're taking some measurements, and as the implementation continues, we'll continue to collect data and additional information will be provided on the implementation, the performance of the UHPC overlay as it gets placed. So just want to acknowledge the NMDOT for the sponsorship of this project, as well as Tran-SET. And yeah, that's kind of an update on what we've been up to.
Thanks a lot, Dr. Weldon. That was really excellent. So this concludes the presentation portion of our webinar, and now I will start receiving questions from the attendees. So right now I don't see any questions. So if you have any question, please type it in the chat box. And also, if you have any comments for the presentations that you would like to add, feel free to unmute yourself and add your comment. So I have a question for Dr. Weldon. So it's asking, is the New Mexico Bridge over I-25?
Yes, that is. It is a bridge over I-25 there in Socorro.
Okay, so I will wait for another minute to wait for any questions.
Hi, Frank. How are you?
Dr. Weldon, this is Frank.
Yes, sir. How are you today?
Good. This is the bridge that doesn't have a lot of traffic. Is that correct?
It's the on-off ramp right there at the north side of Socorro.
Okay. I'll check it out and let you know.
Okay, I don't know how it's going.
Okay.
Did they mix it, Dr. Weldon, did they mix any of that in a truck, or was it all those little mixers?
All of that was done in little mixers.
Okay, all you guys that are doing this research, we got to get this stuff in the mixer trucks. Make it economical.
Yep.
Right.
Very
So
good presentation. Very good.
thank you. So while we are waiting for the questions, I just want to remind all the attendees that we will have all the presentation slides and the recording of this webinar uploaded on our website, and I have added the link for our website in the chat box. So I don't see further questions. So I would like to thank our three presenters for their time and their technical presentations. I would like also to thank all the attendees, and let me know if you have any questions about our webinar series and about Tran-SET. Otherwise, have a great rest of your day. Thank you.